Okay, in this lecture we're going to talk about compound interest, which is an application of exponential functions. Compound interest occurs when we are actually depositing money and we are actually getting interest on interest. Now, the way it works is like this. So let's suppose we take $10 and we're getting, say, 10% interest. So per year, say. And we're going to compound this yearly. So at the end of the next year, you'd have $10 plus the $1 interest, which would make $11. So that's after year one. Now after year two, you'd have the $11 plus the $1.10 now, because we're making 10% on $11. So you can see you're really getting 10% on the interest that you had as well. And we keep doing it this way, and we can build up a formula that says that the amount that you will have, okay, after depositing P dollars, okay, at an annual interest rate of R, okay, compounded this many times per year. Now up here we did it just once a year, but we could do it semi-annually or twice a year. We could do it quarterly, which would be 4 times a year. We could do it monthly, which would of course be 12 times a year, and so forth. And of course time here is in years, okay, and so n is the number of times it's going to be compounded, and t times n, of course. So if we did it for 4 years and compounded it quarterly, it would be 4 times 4, which would be 16. All right, and that's what we have to take the power to. So you can see it's an exponential form. And sometimes this amount that we have, A, is called the future value, and P is called the present value. So let's do an example of this. So find the future value. So the future value, of course, is the amount. All right, and the interest earned if we have $65,750 invested, so that's P. Okay, so let's write down the things that we have. Invested at 5.5%, so that's the rate. And the rate at 5.5% will be 0.055. All right, we don't want to write it as a percentage, so it's got to be a decimal. 0.055. And how many times we're doing it? Well, we're doing it quarterly, so n would be 4 times a year. And the number of years would be 10 years. So if we now put this into the formula, there's our P, that's what we're investing. 1 plus the rate is 0.055 divided by 4. Okay, and now we have to multiply it by n, t by n, which of course will be 10 by 4. So we end up with this being 65,750, okay, by, let's have a look here now. We need a calculator. All right, so here's our calculator. So it's going to be 0.055 divided by 4. All right, so this will be, and then we're going to add 1. So it's going to be 0.1375, 0.1375, and we're going to raise that to the power of 10 times 4 is 40. Okay, so we apply our calculator to this. Okay, so here we go, and we have this one, so we're going to raise this to the power of, so raise it to the power of 40, and we get this, and now times by 65,750, and we're going to end up with 113,535. Okay. 535.18. All right, and so that's what we have for the amount that will be there after 10 years. All right, now, of course, what then is the interest earned. All right, well, the interest is going to be how much we have here minus what we had to start with. All right, and so we get our calculator here again, and we're going to subtract off 65,750, and we're going to get 47,785. And 18 cents is going to be the interest. All right, so that's how we do a future value problem. Now let's turn it around the other way and say, let's suppose we want to find the present value of $5,000 if interest is 4.5% compounded quarterly again for 8 years. Okay, so let's put down what we have. So n is equal to 4 again. R is going to be equal to 0.045. And now the present value is what we want to find, and so A then is $5,000. We're really wanting to know, well, what do we start with to get $5,000 based under these conditions? And T, of course, is 8. So in this case here we know A, okay, and so we have A equals P by 1 plus R over N by Tn. So A, of course, we have is 5,000 equals P is what we want to find, and we have 1 plus R is 0.045 over 4 by T, which of course is 8, times N, which is 4. Okay, so this will become P by, now let's have a look at this calculation now. So this will be 0.045 divided by 4 equals this, add 1. So you get 1.01125 to the power of 32. So if I now take this value here and divide it into 5,000, to the 32. All right, let's have a look and see what we get when we do that. So we've got this, we're going to raise this to the power of 32, which is this. Now we need to invert that and multiply it by 5,000. And this is going to be 3,495.40. So what this is really saying is that if I put away 3,495 cents and $95.40, all right, and get an interest rate of 4.5% compounded quarterly and do it for 8 years, I'll end up with the $5,000. Okay, so that's the present value. Right, now some interesting things happen here, and you'll notice here that if I take 1 plus 1 on n, now this is very similar to this. Up here the rate here is basically 1. All right, and we're doing it for 1 year basically. Okay, and let's suppose we're taking $1. And so really what I have is this expression here. And then I start taking values of n, like 1 will give me 2, value of 2, if I calculate it, gives me 2.25, of 3 gives me 2.37037, 5 gives me 2.48832, 10 gives me 2.59374. So my n's are getting larger. And as the n's get larger, you'll see what happens. At 100 we get 2.70481. 1,000 I get 2.71692. Now notice that right here, alright, the first decimal place is the same. If I now go to 10,000 I get 2.71, and notice now we have two decimal places are the same. If I now go to 1,000,000 I get 2.718, notice we now have three decimal places the same. And so you can see it's starting to tend towards a value. This value is what's called Euler's number. Okay. Alright, and we designate it E. Alright, and it's approximately equal to, it's what we call a transcendental number. It's a non-terminating, non-repeating decimal number. And if I write down a few of the decimal places, there's the ones we got here. And if I just kept going, I'd get 1828, and it just keeps going. Okay, this is what we call Euler's number. Now, the interesting thing is that when we now apply this so that we are actually compounding continuously. So in other words, we've talked about quarterly, that's 4 times a year. Monthly is 12 times a year. If we did it daily, that'd be 365 times a year, and so forth. But what if we did it continuously? We just kept compounding. Then the interesting thing is that this thing here is going towards E, and so our actual amount can be formulated by P by E to the RT. So again, A is the amount or the future value, P is the present value, E now is Euler's number, so it's taken the place of this part in here, okay, and then it's to the rate times the time, okay. Alright, so if we now do this, now the other thing of course is that we now have a new kind of function. So we could have, say, f of x is equal to what we call e to the x. Alright, now what does that look like? Well, e now is, notice, it's about 2.7. So if I was to do, alright, that, alright, then let's suppose that this one was y equals 3 to the x. This one, this would be y equals 2 to the x. Then in between those two, we'd have f of x equals e to the x, because e is somewhere between 2 and 3, because it's 2.718281828 and continually. Alright, so it has the same characteristics. Alright, it has the same characteristics. Opens upwards. Domain is all real numbers. Range is 0 to infinity, not including 0. It's continuous. It is 1 to 1, so there will be an inverse for it. It's going through 0, 1, and so forth. Alrighty, so this is really just another version of the exponential function. In fact, this function here is called the exponential function. It's the very important one. Okay. Alright, so how do we do this? Let's suppose I want to find the future value, so that's A. Alright, and interest earned if I again have $65,750 invested at 5.5%, but now it's compounded continuously for 10 years. So notice here that P is going to be our 65,750. Our rate again is 0.055. T is going to be 10 years, and of course that's all we're going to need for this one here. So this will be A then will be equal to 65,750. Right, E now to the rate, which is 0.055 times by 10. So this will be 65,750 e to the 0.55 now when I multiply by t. Now this is going to come out to be approximately, if we look at our calculator again, alright, it's going to be E now. So there's E. I'm going to raise that to the power of 0.55. This is what I get equals here, and now multiply it by 65,750, and I end up with 113,961. Right, 0.39. Right, now how does that compare? Well, notice here, alright, we had 535.18, now we've got 961. So obviously compounding continuously makes it grow quicker. So the interest then is going to be 113,961, alright, and 39 cents minus the 65,750. Alright, and that's going to come out to be $48,211 and 39 cents. Right, and that's how we do a compounded continuously problem, and you can see that it is a little better, all right, than just compounding quarterly, and we have less calculation really, because we only have two things here to find, and that is multiply the year times the rate and raise it to the power of, and therefore take E and raise it to that power, and then multiply by what we had to begin with, which is the present value.